Okay, so in this lecture we will look at periodic functions, what they are, and some of their elementary properties. Periodic functions are, a basic idea or a basic ingredient, in our discussion of Fourier series, which is coming up a little bit later. But in this lecture we will look at some basic properties of periodic functions. Okay, so we start with this definition. So a function f of x is periodic if f of x plus p is equal to f of x for every x, right? So this is a property that this, there is inherent in this definition also the idea of p, so, and which is the period. So the number p is called the period, right? So immediately from this definition, it's very intuitive, right? So we have come across periodic functions, and again, closely related to the idea of in the context of simple harmonic motion, for example, right? So you have seen periodic functions, and they are ubiquitous in physics. We look at phenomena which are periodic in nature. We also work with systems where you have an external force or a drive which you can you can bring in, and you can bring in a periodic external force, and how the system behaves under the application of such forces are very important ideas, and they appear in all kinds of fields and subfields of physics, right? So periodic functions are are of great importance in physics. Now a periodic function is like what we have defined, and the number p is the period, right? So immediately from this definition we see that if p is a period, then so is any multiple of p also must be a period, right? So typically we are interested in the smallest such p, right? That's what we mean by the period. Although strictly by speaking from this definition, p, if p is a period, then so is 2p, right? Because f of x plus 2p is equal to f of x plus p, which is equal to f of x, right? So it's so we are usually going to be interested in the smallest such p, and that's what we term as the period. So an example of a periodic function we can think of from music, where if you're producing a pure tone, right? Some instruments something like a tuning fork or something which can produce a pure tone of frequency omega naught, and it's perfectly sinusoidal tone, and it has just one well-defined frequency, and then you could represent that with some sinusoidal function. So it's just like in simple harmonic motion, you have a times sine of omega naught t plus phi. But in general, even very elementary instruments, right, so produce much more complicated sounds, right? So if you strike a piano key, you might think that you're just playing just one pure note, but in fact this pure note is going to contain not just one frequency, but it's going to have what is called a fundamental and all multiples of this fundamental frequency, which are called overtones, right? So if the fundamental has some frequency omega naught, you would expect to hear superpositions which are of frequencies 2 omega naught, 3 omega naught, 4 omega naught, so on, and all integral multiples of the frequency of the fundamental are going to be present, right? So suppose you consider these two kinds of functions. So here I have f1 of t is sine of t plus half sine 2t plus 3 sine of 3t, right? So which are just some, you can consider some arbitrary coefficients, right? I'm just considering a harmonic here, and these two overtones here, and a harmonic here, and 3 overtones here, right? You can play with this. You can consider even a larger number, a smaller number of overtones, and so on. So I want to plot these two functions, and so you see, if I here I have plotted this function f1 of t, and then also I have plotted just the fundamental, right? So what I want to observe from this plot, and I have one more plot which is again for the second function, and in comparison with its fundamental frequency. So I see that you know, this, you know, very complicated function which comes from just, you know, the superposition of just 3 or 4 harmonics. Already it looks quite complicated, but you see that if you observe carefully that, you know, there is this repeating tendency, and in fact it's going to repeat exactly like the fundamental does, right? So what you can say is, in fact, the sum of terms corresponding to a fundamental musical tone and its overtones has the same period as the fundamental, right, which we can explicitly verify, right? So if you have a function f of t which is made up of, you know, sine omega naught t plus phi n plus sine of 2 omega naught t plus phi phi 1 and phi 2 and so on, right? So I have a bunch of coefficients which in principle can run all the way up to infinity. So you know, you can have an infinite series of this kind, right? So so the point is that term by term, every term has exactly the same period, right, which we can explicitly verify, right? So defining t is equal to 2 pi by omega naught, we see that f of t plus t is equal to summation over, you know, wherever we have t, we have to put t plus 2 pi by omega naught, and then if you expand this, you see that there is this you know, is the same as writing sine of n omega naught t plus phi n plus 2 n pi, and we know that, you know, the sine function is a periodic function. So if you add an integral multiple of 2 pi to its argument, it remains unchanged. So in fact, term by term, this function is unchanged when you know, increment t by capital T. Therefore, f of t plus t itself is equal to f of t. So in fact, the overall function itself has exactly the same period. No matter how complicated the overall function looks, it is going to be periodic and with the same period as the fundamental, right? So I also want to consider another example where, you know, just like we saw how, you know, functions which look very complicated, apparently very complicated, but in fact they refer to the simple harmonic motions. So likewise here you could have apparently, you know, very complicated looking functions, but actually they refer to just a single harmonic. So like in this example, sine of 2t plus sine of 2t plus pi by 3, but if I invoke the standard trigonometric identity involving sine c plus sine d, then in fact I see that fa of t is the same as sine of 2t plus pi by 3. So although it looks like there are two terms, right, if you have to arrange them properly, and then you can bring it into this first standard form, and then you see that in fact it is just a single harmonic with consisting of just the fundamental harmonic with amplitude a equal to 1 and frequency omega naught equal to 2. And another example is, you know, is this one, where again invoking the trigonometric identity, you can verify that this is just minus square root 2 sine of pi t minus pi by 4. Therefore this too is just a fundamental harmonic with amplitude square root 2, amplitude like we said is necessarily positive, and frequency omega naught is pi, right? So this is just to illustrate that, you know, one must be careful with looking at functions and bring them into standard form before drawing conclusions. So the main moral of, you know, this discussion is that if you have a fundamental and, you know, superpose it with a bunch of harmonics, then the resulting function can be extremely complicated, but still it has, you know, the same period as that of the fundamental. And oftentimes we are interested in the opposite question, which is that you're given a signal which is incredibly complicated, right? And we want to ask if it is possible to think of this very complicated periodic function in terms of various harmonics, right? So this is basically the heart of the Fourier series problem. And then if you're able to express a complicated periodic function in terms of, you know, a fundamental and its harmonics, you know, various coefficients, if you are able to pull out, then you can just work with all these coefficients and understand, you know, what is the contribution of various harmonics or overtones to this problem, and it gives us a lot of insight if we're able to do this, right? So as we will see what is the prescription for working this out, and then we will look at, you know, how gentle this method is and how it can be used. All of this is coming ahead. That's all for this lecture. Thank you.